right. Sorry for the problems. Let's try that again. All right, much better. So I wanted to mention that we eventually want to connect our mathematical study of probability to what we can do with our programs. And there are two examples. One is things like elections, that are inherently probabilistic processes, also all of physics, engineering, social science, and so forth. But the other is we can actually incorporate them in our programs to make them better, more efficient, more robust, and to compute more things. So one question you could be asking within a couple of lectures is, now that we have these powerful probabilistic tools, the ability to use distributions and so forth, is it possible to compute things more efficiently or compute more things than we could before? And we'll gradually dip our toes into this question while learning about probability sum. But just as an example, to give you an idea of this, I want to mention that probabilities and distributions and so forth are actually very well supported within most languages, including Scheme. And so last time we talked about a game that was discussed in the 1600s by the Chevalier de Marais, wrote to Blaise Pascal, who then wrote to Fermat, and asked various questions about dice games. And in Scheme, as well as other languages, there are functions like random. This is a pseudo-random number generator. It's not a random number generator, but it's pretty close. The random function, as you can see here, feel free to blow this up if you can't. This returns an integer value chosen from a basically random distribution between 0 and 6. And so here we can simulate rolling 2 die and asking when we get double sixes. And you can run this, which is kind of cool. So here it took 41 rolls to get a double six. Of course, here we've calculated the analytical probability using this formula of doing the same roll. And here I've done a whole bunch of rolls in a row. So you see there's a lot of variance between these. We can run this again. Here we only got it in 4 rolls. Here we got it in 59. Here we got it in 82. Here we got it in 17. So in some ways, probabilities are a way of getting at the patterns behind this and making predictions. You see there's a very big variance between how many rolls it takes to get double sixes. And it's not surprising that someone in 1654 might be trying to find patterns there and even to exploit them in some sense. So again, random function, very useful. We can use that to model these probabilistic processes in an empirical way, although our focus for the next lecture or two will be more on the question of how to compute things analytically in closed form using mathematics, but eventually we'll augment our programs with these. So there's de Marais' game there. Note that already we're getting into a kind of strange kind of semantics here, if you will. So basically, this is, you could think of this as potentially an infinite loop, right? It's going to call itself recursively and just augment a counter. Like, why should this ever stop? Now, clearly we believe that eventually we'll roll double sixes, but how do we have some confidence about that? So you can ask questions like, well, will it eventually stop? What's the probability it will eventually stop? What's the expected number of rolls until we eventually stop? So all those questions can be asked. We cannot guarantee that weight will always deterministically halt, but we can say probabilistically it will halt. In fact, it will halt with high probability within a certain number of rolls. And we can estimate the probability for each roll as being about 2%, between 2 and 3%. So we have strong ability to predict things here, but already the semantics, that is the meaning of our programs, is getting quite different when we can flip coins and roll die, or dice in this case, because we have a situation here where maybe this doesn't halt, but in fact, in all practical cases, it does. Mathematics is going to tell you you're going to make this halt. So the argument is sort of like you're trying to pull onto the freeway and there's lots of cars. Well, physics and randomness tell you eventually there'll be a slot no matter what happens. But of course, when you're trying to pull on, it might seem like it's taking forever. All right, so a little example of how we can model this computationally using, say, Scheme or another language. We'll come back to this more later. This is especially important when we're trying to incorporate analysis of probability or prediction of probability, or dealing with phenomena from the external world that are inherently based on probabilities in our programs. With that having been said, I want to go back to what we were talking about before and build on it a little bit. So let's share screen from the document camera. I'll go over there and we'll do some math together. Give me just a moment and I'll be back with you. All right, I should be back. Please let me know if you can see the document camera and you can hear me and see me.
Yep, you're all good.
Thank you, appreciate it. All right, so made a little summary of where we were before with our, from last time to build on this a little bit. So one of the kind of cool things we can do is we can start to have a mathematical theory of probability that allows us to actually calculate things really quite accurately. So remember the situation I'm summarizing here. Basically, we have a space of outcomes. Now, I called this S before, but I wanted you to know that in probability theory, this is usually called omega, the big Greek letter. So I'll use omega mostly here henceforth. Now, an event is simply a subset of all the possible outcomes. So this is a set of outcomes omega. An event is a subset. And if we're interested in knowing how likely it is an event will occur, it's basically the size of the event relative to the entire space. And if these are discrete sets with size m and n, it's basically the ratio of m over n, assuming that all outcomes are equally likely. So we're getting into a question today, which is, how do we mathematically define a random experiment? And of course, examples of these include various dice and card games. But using this and using the techniques we developed before, we did a bunch of things. So there's some good notes on the web, at least I think they're very good. I've put up on the web not only the birthday paradox, working out the combinatorics, which are essentially permutations and combinations, which we started to do last time, but I've also put up a short handout on the expected number of different birthdays. I think a number of you were surprised that we actually had 11 pairs of birthdays. Frankly, the TAs and I were also surprised we had no triples. It's also possible to get triples, no triples this year, as far as we know. That's quite interesting. And using this, we can do some rather precise calculations. For example, we can look at Deveray's game with 1 die or 2 dice, and we can correctly calculate the probabilities. The probability of winning is this formula here, about 0.51, 51%. The probability of losing with the 2 dice game is about 0.49. And now we can see an application of probability beyond the mathematical sciences to actually history. So one thing that was claimed is that Demeray was a terrible drunkard and an awful gambler, gambled all the time. And we can't say anything about his drinking from the mathematical record, but we can make a conclusion based on these probabilities to verify that. So in order to see a difference between these probabilities, 51% and 49%, he would have had to gamble a lot. And by a lot, I mean a really huge amount, because it's very difficult to tell the difference between these distributions. If you're doing some kind of scheme and you're winning a lot of money at 51% and losing it at 49%, you are really taking that to the limit. So he must have been gambling a huge amount. And we can actually, so to speak, prove that or see that from the probabilities we can calculate. And this was just done using the tools we developed last time, and hopefully you read that in the notes. So today I'm going to edge into some topics that will continue in recitation, namely conditional probability. We'll eventually get there. We're going to maybe begin setting the stage for Bayes' theorems, which I will really cover next Monday. And I'll talk about an example that is often used as a test at the whiteboard for interviews on Wall Street and also Google and other tech companies. And actually it goes back to a little piece of Russian literary history, namely a novel by Mikhail Lermontov, and I'll discuss that a little bit. Okay. So let's go back to our question raised here about the foundations of probability. So we have a newfound understanding of set theory based on this class, and we're going to use that to show how probability is actually defined and constructed. So we have our idea of events being sets. They're subsets of this big outcome space like this, and we have a calculation what happens if they're discrete, finite, and all equally likely. So more generally, probability attaches to every event the likelihood that will happen. So it's a function on this space here in some sense. And we have to figure out what that means. So when there are finitely many equally likely outcomes, everything is clear. So see this here. And it's very easy to compute things, and we've seen many examples. For example, Desmarais' game and the other card games and things we looked at. However, it's very common in mathematics and also computer science. Infinite sets can be somewhat harder to deal with, but of course you know something about infinite sets now. So the key insight for this first part of the lecture is that probability is actually founded on set theory, and that's why I wanted to teach you enough set theory to understand that foundation. So let's now address our question, how can we mathematically define a random experiment? So think about this. Okay, so for example, we can mean something like, what does it mean to choose a random point within a unit circle? What does that actually mean? And we can actually define what that means and talk about it rigorously. And if you think this is trivial, let me give you another example. So if I ask you, how do you choose at random a positive integer? And remember, at random means all choices are equally likely. So that turns out to be a considerably more difficult question than our question about choosing a point in a disk. So let's begin. We have some steps to take here. So I'm going to try to get at this question of really how is probability founded in order to give you some tools by which you can calculate the answers to specific questions. So to sort of tell you how probability is created and made up, I'm going to define what's called a probability space. So what this is, it's a set of three things, or a triple in mathematics. Think of it as a list of three things. And let me tell you what these things are. So omega, curly f, and p, which would be something like probability. So what are these things? Omega is a set which represents the space of outcomes. Sometimes called the sample space. Now, what is this curly calligraphic F? This is a collection of events. And remember, every event is a subset of omega, i.e., a set of subsets of our outcome space omega. And by our newfound knowledge of set theory, we can write this as F is a subset of the power set 2 to the omega. So it's some set of subsets of this. So please compare this to midterm 2 and PS5 and other places where you're seeing this. From this, we can conclude that if we have an event A, which is in our collection F, it's necessary that A is a subset of our set of outcomes. This raises the question, what if we have an arbitrary set A, which is just a subset of our outcomes? Is it an event? And here the answer is a little more complicated. So the answer is, in this class, yes, because I'm going to give you well-behaved examples. But there are good reasons for not assuming so in general. So in other words, our set of arbitrary event in our set of events is necessarily a subset of our outcomes. But the other way around is not necessarily true in general, and you'll encounter this in future mathematics classes. Now, we now want to ask, what are the properties that we have to satisfy with F in order for it to be sort of well-behaved? Now, I'm going to be very high level about this. Many of you will want to take a course in measure theory later to understand what's really going on. But what's important is the following. We want to be able to take the complement of any event. So if we have the complement of an event A, which of course is defined by the set difference of the set of outcomes in A, this also has to be in our space of events if A is in the space of events. So in other words, if A is an event, its complement is an event also. And we have to be able to take unions of two or more events. So in other words, we want to be able to write down the union of event A1 and A2. And this happens whenever A1 or A2 happens. And we want to be able to take intersections, namely A1 intersect A2. This is an event that occurs when both A1 and A2 happen. And so the language of probability is transformed into the language of set theory. The opposite or complement of event is merely the complement taken like this. Either event happening is a union, both events happening at the same time is an intersection. And we just have to construct this in such a way that everything is well defined. Okay. Now I need a definition that's technical. Technical doesn't mean difficult, but it means fundamentally not of interest by itself. I'm going to imagine that I have a series or a set sequence, say, of events, A1, A2, and it can be infinite. And I'm going to call them pairwise disjoint if pairs of them don't intersect. Let me write that down. So we are going to say we call events, let's have an infinite series, A1, A2, all the way up to infinity. Call this set of events pairwise disjoint. Which in this lecture I will abbreviate PD, but that's not a standard mathematical abbreviation. When, what happens? AI intersect AJ is equal to the null set if I is not equal to J. So every pair of these has no intersection. Finally, given this, we can define probability is. So notice what we've done is we've defined the space of outcomes. We've defined the collection of events here, and they satisfy some rules. We can take complements, unions, and intersections and still get events. That's exactly what we want. And finally, we have to define what the probability here, which is going to be a function. So the probability, P, is a function taking each event to a real number. And it satisfies several properties, which are called axioms. So let's label them. Axiom 1. So the first is for any event A in our collection of events, we have that the probability of that event is greater than or equal to 0. Can't have any negative probability events. And axiom 2 is another well-behaved things. The probability of the entire space is equal to 1. So the probability of the entire set of outcomes is equal to 1. And axiom 3, which is the most interesting and most powerful, is again, if A1, A2, all the way up is a sequence of pairwise disjoint events. Remember, pairwise disjoint is defined here. Then we have that the probability of the union of these events, the union for I equals 1 to infinity of AI, is equal to the infinite sum I equals 1 to infinity of the probability of each one of these. So let's look at this. There's a lot going on here, but you're all prepared for it, given what we've done. So this beast on the left, this is a countable union. And this beast on the right is an infinite sequence. So obviously it's accessible here via streams and accumulate. So this is one of the reasons I wanted to teach you streams and countable unions. And the reason is that probability is the foundation of all statistical inference, all AI, all machine learning, many parts of science. In order to understand how probability works and compute with this, you actually have to know what countable unions are and infinite sequences and how to manipulate them. And that's why we spent some time talking about those creatures. But in particular, one thing we can conclude from this definition of what probability really is that we can see that in some sense, we have information already. So this probability function here, which really does give a real number for each event, in other words, P of A is an event, we can conclude from this in relatively few number of steps that actually the probability function could be written as just a mapping from events to the unit interval, because probabilities are bounded between 0 and 1. So that's kind of a nice simplification. Now, whenever we have an abstract definition like this, no matter how powerful, the first thing we want to do is to look at some examples. And so I'm going to do that, but of course, we'll come back to this as we need it. So example 1. Let's look at that should be a 1. Let's look at a space of outcomes corresponding to a single die. So we have 1, 2, 3, 4, 5, 6. The probability of an event, which is a subset of omega, is simply the number of elements in A divided by 6. And that's a perfectly good probability function. So here the random experiment is rolling a fair die. And for example, A could be the resulting value is even, the resulting value is odd, the resulting value is a prime number, or the resulting value is 6. Let's look at another example, a little more interesting, and relating back to what we introduced with. So you can think of this as a problem of throwing darts, and it's continuous, but it has many discrete aspects. So suppose we wish to pick a point from inside the unit circle. Okay, so conceptually, we have something that looks like this. We have our unit circle, looks like this. We want to pick a point from inside the unit circle. So here our space of outcomes is just a set of points inside the unit circle. Let's write that out. We have x comma y in the plane such that x squared plus y squared is less than 1. Good. And sometimes in mathematics, this is called B2. So it's the disk or the ball of dimension 2. All right. Now, suppose we have, what does an event look like here? That's a really interesting question. So an event might look something like this. It's some subset of this, right? So an event is this set here. And of course, omega is the set of all points inside the unit circle, like that. And an event is some subset of the circle, nicely drawn like this. So the probability of the event A is simply equal to the area of A divided by pi. Now, it's important to note that in the case where A was not such a nicely defined set, but was actually a singleton, by which I mean something like this, if A is equal to the single point x comma y, and we'll make that a set, then the probability of that event is 0. And this means that we really can't attach a probability to outcomes. We can only attach them to events, which are the subsets of outcomes. And one way to think about this is if you're throwing darts at a disk, namely a dartboard, the probability that you exactly hit a single point is identically 0. But with any kind of fatter set with positive area, like a bullseye, you'll hit with positive probability. So this is a key lesson here. This is why we don't define probabilities directly on outcomes. It's why we define them instead on these sets, which have measurable area. All right. Now, you might ask, okay, that's great. I sort of see the idea. What if you take an arbitrary subset of the disk, and we've made some pretty crazy subsets in our time, even in this class, is it possible to always assign a probability to it? And the answer is, in this class, yes, but in general, no. And Cantor, the great mathematician who also worked on undecidability, he showed that there's a special set or family of sets called the Cantor sets, and you cannot define the area or probability of those in a way that makes this work. So it's only certain sets, and you'll learn about these in a later math class. But we're going to exclude those for our purposes. They don't come up practically in engineering, for example. And I'll tell you the sets that I give you and that you'll make will be ones that will be things that have area and you can assign probabilities to. And there's nothing wrong with looking at an outcome, it just will have probability 0, because there's no chance that you'll exactly hit any particular point on the dartboard. Okay, now the next thing we'd like to do is be able to compute some things with these axioms. I mean, these axioms are a little bit abstract, although extremely powerful, it will turn out. So I want to be able to take these ways of setting a probability and give you some formulas that you can use to compute probabilities, and we'll prove some of them. Other ones we'll ask you to prove. So let's actually do that now. All right. So I'm going to call these consequences of the axioms of probability. And our goal here is to write down some formulas to compute with and also to understand why they're true. So let's write this one down first. C0, consequence 0, is that the probability of the empty set is equal to 0. We can derive that from the axioms. I'm going to ask you to do it, and we're happy to show you the results. Try that as an exercise. We'll come back to it. Ask you. How about C1? So suppose I have two events or sets. They're obviously subsets of the outcomes, A1, and they don't intersect. So A1 and A2 are events, and they have no intersection. Then I can write that the probability of the union of those, that is the union being one or the other occurring, is simply equal to the sum of the probability of the first plus the sum of the probability of the second. Let's just take a minute to prove that, see what we can do. So what I'm going to do is I'm going to employ my very powerful Axiom 3. So I'll slide that down here so you can see it. So Axiom 3, now notice I have these infinite sequences here. If I have an infinite sequence of events that are pairwise disjoint, then I can compute the probability of the union by the sum of the individual probabilities. So what I'm going to do is I'm going to apply Axiom 3 to the sequence A1, A2, and then null, null, null set all the way up to infinity. And if you do that, the identity pops out, which is pretty cool. It's a very powerful, powerful axiom. Let's look at C2. There are only 5 of these that I'm going to do today. Suppose we have an event A, and we take its complement, and we ask, what is the probability of the complement? Well, this is simply equal to 1 minus P of A. So the probability of the complement of A is equal to 1 minus the probability of A. Let's prove that too. So to prove that, I'm going to actually use C1, which I just proved here. I'm going to apply C1 to, well, C1 takes as input two sets A1 and A2. So I'll let A1 equal A, and I'll let A2 equal A complement, and I'm done. Okay. C3 we've already sketched. You can come up with a proof of this. It says that probabilities are bounded between 0 and 1. So if the probability of an event A is always greater than 0, always less than 1, I'll let you prove it. I want to say 2 more. These 2 are given in the notes, but try to prove them yourself. They're extremely powerful for computing, and they're things that are fun to prove, although they're not that fun to listen to someone prove. And since I want to have fun in this lecture, I'm going to let you all prove them. But I'll state them, and I'll tell you where to find them in the notes. So the first situation looks like this. Suppose we have two sets with this relationship. This is my set B, and this is my set A like this. And I want to know about the probabilities of these two sets. And I'll write this as if A is a subset of B, as I've drawn here, then the probability of B is equal to the probability of A plus the probability of B minus A. And this is always greater than equal to the probability of A. So it kind of makes sense. I'll let you prove it, but basically it says you want the probability of B. Well, compute the probability of A, which is this region here, and then compute the probability of B minus A being all of this square here except for A, and then add them together. C5 is similar. Again, the proof is in the notes. Try to prove this yourself. Ask us if you're confused or you get stuck. Then check yourself in the notes or iterate till you get it. Also very useful. So the scenario here looks like this. Suppose we have two events, say A and B like this, that may have some intersection like this. And we're interested in the probabilities of A and the probabilities of B and how they relate. So this says the probability of A union B, that is the probability that either A occurs or B occurs. This is simply equal to the probability of A plus the probability of B minus the probability of their intersection. Now, one way to think about this is probabilities aren't areas, but they're a little bit like areas. They're both measuring things. So when you think about the intuition here, the intuition is think of probability as some kind of area here. The area of A union B is equal to the probability of A. Sorry, the area of A plus the area of B minus the area of their intersection is equal to the area of A union B. Similarly, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of when they both occur. Similar intuition can be used for C4. Again, if you think of probabilities as areas, the area of B can be written as the area of A plus the area of B minus A. We can map those all to probabilities and have at least make intuitive sense. But to actually prove it, you have to work through the axioms and see if it works. So this gives us some very nice techniques for computing probabilities in the case where we have sets that are disjoint, we have complements, we have sets that are subsets, we have sets that may or may not overlap. So this gives us some calculational tools, all based on the axioms of probability. So a way to think about this in terms of what we're learning in the class, to understand probabilities, we need set theory. So things like A intersect B, and we need an understanding of functions. Things like the probability function here and how they work. And this is one reason that I taught you these things, even though we actually need some somewhat advanced concepts in set theory, such as countable unions, to make sense of this. So without the understanding of set theory and functions, we can't understand probabilities. Once we do understand probabilities, we have the entire basis of statistical inference, AI, machine learning, and Bayesian reasoning, which is what we want to be able to get you to. All right, so in short, we have some calculational rules which derive from the axioms. I proved two of them for you. I sketched another. The rest are given in the notes. Try to prove C4 and C5 by yourselves so we can do some calculations. Oh, try to prove C0 also. It's a good exercise. All right. All right, so this is a little abstract, many things, many tools we're learning here. What I would like to do is to do some examples now, certainly before we get abstract again. And the example that I will do first is called conditional probability. So of course, this is a mainstay of probabilistic analysis, Bayesian probability, lots of things, but also be extremely useful in problem set 6, which will be out next Monday after problem set 5 is due. So let's take an example, a very, very simple example. So in this example, we again have the notion of a random experiment. And the setup of this is I have a bag, an opaque bag with cubes in it. Think of children's cubes that little kids play with. And the cubes have different colors and they have different textures. And the setup of this can be thought of something like this. So I have a bag that actually has 11 cubes in it. And some of these are fuzzy, 11 cubes. I have 7 of these that are fuzzy. And 4 of these are smooth. And they have different colors. So of the fuzzy ones, 3 of them are red. And 4 of these are blue. And of the smooth ones, 2 are red. And 2 are blue. So already you can think of these cubes and the collection of these things. We can already start to write some things down. So without knowing any more information here, there are 11 possible outcomes, which are the different cubes when you reach in to pick something up. And without knowing anything else, we can see that the probability of getting a red one is something like 5/11ths, right? Because 5 of the cubes are red and the rest are blue. Namely, there are 5 red cubes and 6 blue cubes. So here's what happens in our random experiment, which has a couple of parts. So note that before we started the experiment, before we reached into the bag or did any measurements, the probability of getting a red cube at random is 5/11ths, right? So you plan to pick a cube at random. You'd like to pick a cube at random, but you forget to wear gloves, right? And you stick your hand into the bag and you grab a cube without your gloves, and you notice that it's fuzzy. And your hand's in the bag now, but you don't look at it, right? So all you know is it's fuzzy. So clearly the probability of having a red cube in your hand should now change to 3 out of 7 because you have more information, right? So how do we model that? It turns out conditional probability, which is built on what we've done, comes to the rescue. So let's just write this down. So the experiment, everything is discrete. We have 11 outcomes because there are 11 cubes in the bag. And we have certain events, which is our set F, and I'll call these red, blue, fuzzy, and smooth. And of course, all of these are subset of my outcome space, right? Subsets, that's a subset sign of the outcome space, right? Let's sort of draw this a little bit, see how this would work. So this is my fuzzy column, smooth column, red row, and blue row. And just to kind of reify this a little bit, I'll actually put number of points in here, 2 points, 2 points, and 4 points. So this is a map of our set of outcomes and our set of events here. And of course, you can clearly see that the probability of having a red cube is going to be 5 out of 11ths, because if you go to this top row here, we have 5 elements just as we had in our little decision tree. Okay. Now, in our experiment, we reached into the bag and we got a fuzzy cube. We need a notation for this. We need a way of calculating. This is called conditional probability. So for the probability of getting a red cube conditional upon its being fuzzy, we write a new notation. What we're going to do is we're going to write the probability of getting a red cube given that it's fuzzy. Conditional it's fuzzy equals 3/7. Now we can actually define what that means, and this is a general formula. This is equal to the probability of our intersect F, namely of the events red and fuzzy occurring at the same time, divided by the probability of being fuzzy, like this. And one way to think about this is to go back and see how these various intersections and such sets relate to our little diagram here. So remember that red is the entire top row here, blue is the entire bottom row, F is this entire column, S is this entire column. And now what I will do is I'll make these lines firm, and we'll just annotate this as being, this is the event R intersect F. Here we have R intersect S. Here we have blue intersect fuzzy, and here we have blue intersect smooth, right? Because we're intersecting rows and columns. So these are the various events and their intersections here. So what this notion conveys is the idea that with additional information, the probability has to be adjusted. And this is called, I guess, the definition of conditional probability, which I'll sometimes write like this. Just like PD, this is my notation. The CNDX is an engineering notation that is not standard in mathematics. You can write out conditional. So let me philosophize for a minute. This is very common in real life. So let's take a sports metaphor back when we were all attending big sports events and enjoying them. Suppose you're betting on the Duke versus UNC game, right? And the chance of Duke winning a priori is 60%. And suppose an hour before the game, a star center for our team sprains her ankle. So you cannot expect the odds to remain the same. And a bookie would change them at that point to 0.3. But nevertheless, Duke plays really well. And by halftime, Duke is up by 25 points. And so now the odds of winning change to 80%. And of course, when the game is over, the probability equals 0 or 1, since it is decided. In this case, of course, we want Duke to win, so it'll be 1. So you could imagine graphing probability over time based on the information we have. So as I mentioned, probability has to be between 0 and 1, and we have time going along this axis here. When we started our little skit here, the probability of Duke winning a priori was 0.6 or 60%. Now before the game, however, this is 0.3, star center sprains her ankle, probability goes down. But by halftime, things are looking pretty good, it goes up to 0.8. And then of course, by the end, Duke is 1 and it goes up to 1. So the probabilities are being adjusted over time like this. And I will also mention we've looked at various views of state in this class, local state, streams, and so forth. This is another view of state, namely a stream of probabilities, in this case, a finite stream. The other thing I'll mention is that this formula is completely general. This is actually the definition of conditional probability for arbitrary R and F, not just fuzzy cubes and smooth cubes. So this is called the conditional probability of R given F. Of course, you could substitute other values for this. All right. So again, despite the maybe accessible examples, we might be still a little bit abstract. So let's do another example. I hope you'll like this one because it's used a lot in interviews. It's become rather popular over the years, although it was less well known when I first started talking about it. So this is a bit of a grisly example, trigger example. It involves a game of Russian roulette. Again, very popular question to ask this in Wall Street interviews. Google asks this a lot too. So first question for you all. Russian roulette. What do you think Russians call Russian roulette? Any ideas? Yeah, there's some ideas that it's called R roulette or roulette. Actually, they call it American roulette. Kind of surprising. So basically, at least in 19th and early 20th century, they called it American roulette because it basically referred to a popular American, what they called cowboy culture. And if you know anything about the history of the former Soviet Union and of the czars before then, revolvers did not exactly freely circulate in Soviet Russia or pre-Soviet Russia at that time. They were pretty rare. The nobility had them, but generally they weren't around very much. Duels were done with single shot revolvers, for example. And if you look at this sort of in a historical sense, there's actually only one source referring to Russian roulette before the 20th century. And this is in basically a book by Mikhail Lermontov called A Hero of Our Time. Герой нашего времени. Which actually contains some novellas. There's a long novella in here called The Fatalist. In which basically a minor character called Pechorin survives what you could think of as a version of Russian roulette, after which he has a revelation and decides not to be an atheist and embrace the Orthodox Church and live a good life after that. So anyhow, Mikhail Lermontov, famous Russian writer, Герой нашего времени, Hero of Our Time, The Fatalist. This is around 1840. Yeah, so they call it American roulette. I don't know what they call it now. So this is interesting. We're just going to continue to call it Russian roulette. Apologies to the Russians. So here's a very macabre example, again, popular in interviews. And I'm going to ask you which you choose. You get a choice here in this Imagine Your Interview. I'll ask you to raise your hand or shout out your answer, and then we'll work the probabilities. So in this game of sort of Russian roulette, we're going to have a revolver with 6 chambers for the bullet. And we're going to put 2 bullets in the chamber, and they're in adjacent chambers next to each other. And you're forced to spin the barrel, therefore randomizing the position of the hammer. And when you do that, you then have to put the gun to your head and pull the trigger. Thankfully, you don't die, and the hammer falls on an empty chamber. And now your interlocutors in your interview are going to give you a choice. You're going to have to pull the trigger again, but your choice is, do you spin the barrel first and then point it at your head and shoot? Or do you simply shoot again? Now we assume that the revolver just keeps rotating, say counterclockwise. So the choice is, you're going to pull the barrel again, you're going to pull the trigger again. It's going to point it at your head for a second shot. You've survived the first one. Do you spin the barrel again, or do you just pull the trigger without spinning? So spin or pull without spinning? What do you say? Which is safer, or which is more dangerous? Some answers. I only see one answer. Some people say spin. Some people say don't spin. All right. All right. So why? That's okay. So lots of great ideas about this. So why would it be? I think the intuition why spinning might be a good idea is pretty clear. You kind of randomize things. But why would not spinning be the right thing? What's your argument? Would anyone like to tell me their reasoning? Why would that make sense?
I'm trying to equate this to the problem that I've heard about where it's like what's behind door number 1, 2, and 3, and given information about the door you already know about, it is in your best interest to almost build off of those odds. Because I would say if you just spin it again, then it's randomized. But given the pre-existing information that you have, I believe it's in your best interest to not spin again.
I mean, certainly that problem, I mean, basically that problem is more related to the fuzzy dice problem in some ways. So certainly it's the right set of tools to use. But the randomization is a little subtle. Like that's called the Monty Hall problem. And we typically do that in recitation, not this Friday, but next week, which is a very fun problem. So it does relate to that for sure, but the randomization is a little bit different because in the case of the Monty Hall problem, you're not necessarily randomizing. So it's right intuition for sure. Does anyone else have ideas about why you should or should not spin? Tell me your reasoning.
I feel like if you don't spin, if you spin, there's 2 in 5 chance. I mean, there's still 2 in 1/3 chance, I guess, that it's a bullet. But if you don't spin, then there's 1/4, because the following could be 3 empty or 1 bullet, I think.
Yeah, that's basically the right calculation, I think. So let's work it out. It's kind of surprising, in some sense. So I think you basically got it. I'll try to work it out, and you tell me if I've got the right idea. All right. So let me draw a little picture here that always helps me. Remember, picture is not a proof. So here's our revolver chamber. Not equal, like this sense. And we're set this up by we're going to put bullets in these two here. So since bullet 1 goes here, bullet 2 goes there, and then we're going to spin this. So you don't know which one you're on. And I'm going to assume without loss of generality that the barrel rotates, say, counterclockwise, just has to be consistent after the hammer's pulled back. So in this situation, as our colleague just described, you're given the choice between the unconditional and conditional probability of death. Right? That's what you do here. So let's calculate this. So by the way, this is a somewhat subtle question. I think you all are doing really well. So I've been interested in this question for a while, and actually during our holiday party in computer science for faculty and grad students, they asked this as a prize, and a number of distinguished faculty got it wrong because it is subtle. It's tricky to get this right. So let's try to do it. It's not complicated though. So we're, again, in this situation, the way to think about it, and this is related to the comment about the door problem, do you get the goat or do you get the washing machine? It is related to the Monty Hall problem in its mechanism, but it's not quite the same. So you're basically given the choice between unconditional and conditional probability of death. That's really what's going on here. So I'll write it out like this. The unconditional probability of dying on second shot, and no, basically, if you spin both times, is equal to the following. Probability of dying is equal to 1/6 plus 1/6, which is equal to 1/3. Now notice we're not adding probabilities between two rounds here. So look at the drawing here. This is the probability that our hammer lands on the first bullet. This is the probability that our hammer lands on the second bullet. They're independent, so you add them up. So there exist 2 bullets, bullet 1 and bullet 2. So if you spin it, this is your probability of dying actually in each round. This is after your first spin, your probability of dying was 1/3, but you survived that. Second round is completely uncorrelated because you spun again. Your probability of dying in the second round is also 1/3, because the only thing that matters is, does your hammer land on a bullet? And 1/3 of the slots have bullets in them. Okay. In contrast, what happens if you don't spin? So this is conditional probability. So when we pull the hammer the first time and we go click, we know at that point we're on one of the empty chambers, one of these 4 here, but we don't know which one. We know that there are 4. Now we assume without loss of generality that the barrel rotates in some fashion. Say it rotates clockwise, doesn't really matter. But the key thing is that now we're on an empty chamber because our hammer just clicked on an empty chamber. And now we're going to rotate. So only one of these is next to a bullet, 1/4 of them. So the probability of dying in this case is only 1/4 because only one of these chambers is next to it. So therefore, you should not spin the barrel before pulling the trigger the second time. So again, in this case, conditional probability reflects the probability that the hammer clicked on an empty slot while being next to a bullet. So kind of surprising in some ways. Any questions about this?
It's just a quick question. So does when you pull the hammer, why can't you just pull it in the same position it was on, which was empty? I mean, does it move at every pull?
Yeah, it's part of the mechanism of a revolver. So now it's basically that a revolver never works by firing the same chamber. So after it clicks, it always rotates. So you can't decouple those two things. Make sense? Hello?
Yeah, but
Yeah.
though you did say that the probability, that you said that only one space is next to a bullet, but isn't there two slots that are next to a bullet?
Yeah, but it only rotates in one direction, right?
Yeah.
It rotates consistently. So one will rotate away. So depending on what your convention is, if you're here, you'll rotate onto a bullet. If you're here, you rotate away from a bullet, right? They have to rotate in the same direction. They can't rotate arbitrarily. Do you believe it? Make sense?
Yes. Thank you.
Okay, good. Yeah. So we get to combine a little bit of the mechanics of firearms together with the glass. All right. More questions on this example? All right. So very powerful, also very good interview question. All right. Let's do a little bit more. I think I need some more paper. Firstly, I have it right here. So I want to give you another powerful calculational tool that will be very useful when I cover Bayes' theorem and applications next Monday. So this is most properly called the law of total probability. But it's sometimes called Bayes' first theorem. I'm going to use the first because Bayes' second theorem is the one that most people know. And this can be illustrated as follows. So imagine we have a set of outcomes that looks like this. So this is our omega space. And we're going to divide these up between different events. And these events are not only pairwise disjoint, but the union of all these events equals your omega space, or your space of all outcomes. So we'll call these events F1, F2, F3, F4, and so forth. It doesn't matter how many there are. So again, they're pairwise disjoint, no pair of them intersect, and also their union equals the entire space of outcomes. And I'll do an example in a minute. So the theorem is, assume F1 up to Fn, everything's finite here, are pairwise disjoint, and their union, F1 up to Fn, equals all of omega. Now, I'll write an IE here, but it's not needed mathematically. Exactly one of them always happens. So this is sort of the phenomenological description of probability. Exactly one of these things always happens, right? But this is the mathematical way. These are events, events are sets, so that's how we set it up. But that lets us calculate. Okay, assuming that's the case, now imagine we have an event A, which I will simply draw like this. And A doesn't have to be anything in particular, it just has to be an event. Then, for an event A, we have the probability of A is equal to the sum for I equals 1 to n of the probability of the frequency Fi times the conditional probability of A given Fi. Okay, now we're going to prove this, or let you prove it, but first I want to sort of motivate why this would be a good thing. So let's look at two examples. So I'll take an example from social media. So, you know, when you do social media, Facebook, TikTok, Instagram, and other things, it has this thing it wants you to fill out, age and gender and so forth, or I don't care to give that information. And when Facebook first came online, there were only two genders, male and female. By 2006, there were 8, and now there are 56 plus I don't care to tell you, or I'm not on the list. So we're going to consider the initial version and the version of 8, just because I can draw 8 things here. So imagine a world that has multiple genders, and the property A is an individual has blue eyes. Now, in a hypothetical world that's binary, such as 2004 on Facebook, F1 could be the event that the individual is male, cisgendered. F2 could be the probability the individual is female, cisgendered. And using this calculation in the first example, this simply tells us that the probability of blue eyes in an individual is simply equal to the probability of the frequency of being male times the probability of having blue eyes given the individual is male, plus the probability or the frequency of being female times the probability of having blue eyes given that the individual is female. So in a binary world, it works out like this. Now, if we have other genders, so again, F1 is sort of the frequency of being male, the probability here, F2 female, we can add in the other genders to be whatever, however they're listed, and then we can continue the sum. The third thing is the probability being gender 3 times the probability of having blue eyes given that you're gender 3, and so forth, all the way up to 8. So it's a fairly natural construction here. So basically the events have to form a partition here. And given that they form a partition, we can calculate probabilities very nicely. Again, the law of total probability, extremely useful in the future. I'm going to say that you have all the tools to prove this, but what I'd like to do is to suggest try to prove this. Because what I'd really like to do is illustrate some cases that we'll be looking at in the future, do something a little more interesting in this case, and then we'll help you prove it. There's also going to be a proof in the notes. Okay, so law of total probability here. We've done examples 1 and 2. Example 1 is the binary case where there are only 2 genders. Example 2 is the case where we have many different choices here. The main thing for this example, they have to be mutually exclusive. You can only be one of them at a time. All right, so there's a law of total probability. So let me sort of hint at some things that I want to do, edge into in the future. So we'll do some things here. So we'll mostly get into this next Monday. I think it's worth talking about a little today, and I'll review again. So here is a nice cartoon from XKCD. I'll let you look at that for a minute. And this is generally graces the office doors of a majority of statisticians and probabilists. And the point of the cartoon is to talk about differences between two classes of statisticians, or two approaches, frequentists and Bayesians. I'm not going to get into that. We just want to understand the Bayesian calculation here behind this. So to mathematicians, this is a funny joke. And essentially what we're going to do is we're going to pull all the petals off the flower in order to prove that it is hysterical. So let's do a little background to make sure we understand what happens. So we're building a neutrino detector here with some probabilistic things to detect when the sun has exploded and gone nova. And it's dark, so you can't actually see it. You're on the other side of the Earth. I'd like to ask, in order to understand this joke, do you understand why we want a neutrino detector for this? Who would like that explained? Yes, okay. So high-level explanation is that when a star goes supernova, there is an enormous explosion of neutrinos that actually reach any detector before the light and heat and blast wave. And this has been experimentally confirmed in deep underground where we detect neutrinos. The neutrinos arrive a little bit before you can see them by light, which is amazing. So neutrinos are very tiny. If I look at my thumb, in any second, there are about between 1 billion and 1 trillion neutrinos that pass through it, most of which without interacting. Let's just do a little physics anticipating this question. So here's what's called a Feynman diagram of a very common phenomenon you might have seen in nuclear physics. And this is what happens when a neutron decays into a proton. So it makes sense. Neutron has 0 charge, proton has charge 1, electron has charge -1. So the charges add up. So the neutron decays into a proton and an electron, but it also emits what's called an anti-neutrino. That's kind of a weird thing. And you can see what happens here in the Feynman diagram, which I don't assume you've seen before, but time goes like this, and we see how the particles evolve. So a neutron is made up of 3 quarks. In order to do this conversion, what happens is, over time, one of the quarks changes flavor from down to up. It emits this particle here, which is called a W boson, which then decays into an electron and an anti-neutrino. So sort of chemically, so to speak, in quotes, it looks like this. The neutron decays into a proton, an electron, and an anti-neutrino. How does this possibly relate to our supernovas? Well, all physics is reversible. And as Tim Robbins said in The Shawshank Redemption, it's the study of pressure and time. So given enormous pressures, enormous energies, enormous time, this reaction can be reversed. And in a collapsing star, we can neutronize protons. Things go in the opposite direction. In that case, basically the protons are transformed. Things go in this direction, we get neutrons out, protons go in, and we emit neutrinos instead. So what happens in this case is, in some sense, that a proton and an electron get compressed together to make a neutron. That process emits a neutrino. And that's what happens in a supernova, which is pretty amazing. So back to our example here, from a functional point of view, a huge swarm of neutrinos is going to hit our detector. And suppose we attach something to our computer that can detect that. So what happens here is we build a little device here that what it does is it basically interrogates the neutrino detector, which is a sensor, and asks the neutrino detector whether or not it's gone nova. And if it does, after that, it rolls 2 dice, just like Desmarais. And if they come up 6, it lies to us, otherwise it tells us the truth. And based on how you interpret probabilities, you might be worried in various different ways about this. So the frequentist says the probability of this result is just like with Desmarais, about 2%. Probability. So I'm going to conclude the sun has exploded. And the Bayesian uses the prior information, which I will tell you about, in order to conclude that this is extremely unlikely. So we'd like to sort of understand what's going on here. It's really combining several things in order to have humor. the notion of Bayesian statistics, which I will teach you about on Monday, followed by the idea of building a machine that is somewhat computational. The machine involves randomness in some sense. So what I want to convince you of is that when you have a joke that maybe you don't understand, that it is a very engaging process to write out mathematically what's happening in the joke, and then you'll be able to laugh at it much better. So let's extend Desmarais' game by writing some code. So here's Desmarais' game. Remember what he's doing here is he's rolling 2 dice, and he's waiting till he gets double sixes, i.e. just 6 equal random 7, random 7. Random 7 returns an integer between 0 and 6. That's fine. So we want to know when that happens, right? But our neutrino detector is actually working the same way, and we can write that modularly in the following sense. So we have a function here, we don't know what it does, called neutrino storm. And basically we call that, we get a Boolean back and load that into our variable exploded. Then, as described in our cartoon, having measured that variable, we then roll 2 dice, like this. And if the dice come up double 6, we lie. We give the opposite of it, otherwise we tell the truth. So this strange machine that we built actually can be implemented in Scheme. Of course, we have a little trouble implementing the neutrino detector unless you want to go deep into the mines above the deepest mountains in Japan, or you want to go to Antarctica where they also have such a device. But let's assume we have such a thing. You could actually implement this and analyze it. So what we're talking about here in understanding this joke is essentially, can we come up with a way that we can take a joke like this, map it, so to speak, onto code, and using the same kind of techniques that we used before for things like a substitution model, figure out what really happened here. And so to make this slightly less frivolous and irresponsible, suppose this really was your machine, and there's some chance that it might lie. What we'd like to be able to do here, we'd like to be able to figure out, given the information this machine gives us about whether or not the sun has exploded, how much to trust it. In other words, how much to use statistical information to make inferences about whether or not the sun exploded. So in short, just given the information in this cartoon here, we can write a piece of code like this that then can be analyzed. Then using essentially conditional probabilities, but dressed up in a fancy way that is called Bayesian statistics, we can then analyze what the results of this machine are. And we can say, well, if it says yes, what's the probability the sun has actually exploded? Or if it says no, what's the probability that the sun has actually exploded? So in other words, we can, in some sense, back propagate the probabilities through this code in order to understand that. And of course, then we can also laugh at the joke because we all understand it. So this is just an introduction to this. All I suggest for now is that in your own time, look at the cartoon and see if you think it's funny. I will go through this in considerably more detail and do the calculation on Monday. And we'll be armed with Bayes' second theorem, which is very popular in statistics, machine learning, and statistical inference. And this will be our first example of doing that. So we can make a transition from analyzing things about card games and dice and fuzzy red cubes to actually thinking about what happens with machines and programs in order to understand what we can infer about the conditions that cause them to say true or false, with some idea that that could be important in the case that true or false gives us information about some really big event, such as has our sun exploded. I also want to mention that anything I said about physics is strictly for your entertainment. I think physics is really interesting. You should definitely take some courses in it. You do not need to know Feynman diagrams, beta decay, or four-tailed Feynman diagrams for neutronification of particles. All you need to know for understanding this lecture is that if the sun explodes, there'll be a swarm of neutrinos, and we have an oracle that might be able to detect it in this cartoon. So don't be alarmed. Although if you want to argue with your advisor, you should get physics credit for this class. I won't object. And in fact, on that note, let me mention that having completed the structured interpretation of computer programs, your textbook, Jerry Sussman then went on to write a very famous text called The Structure and Interpretation of classical mechanics, where he basically encodes all the major problems in classical mechanics, that is physics, in scheme in order to understand what these things do. And then he went to Caltech to collaborate on building a supercomputer that decided the problem of whether or not the solar system is stable. Namely, will the solar system fly apart before the sun explodes? Very interesting story, and not so surprising that such powerful techniques like lambda calculus and functional programming are applicable not only to problems in finance, computational biology, computational geometry, robotics, but even to problems in physics that have been studied by some really smart people all over the world. I think with that, I'm going to say I enjoy talking with you about this. I look forward to going into more detail about this cartoon example in Bayesian statistics. I'll do that on Monday, and recitation on Friday will be about the probabilities we have covered and some helps with the computations. Okay, I'm going to stop recording now, and I'm going to stay around as I usually do and take questions. And I'd be happy to discuss probability or any other aspect of the class with you. So good. All right. Let's stop sharing and let me pause the recording.